Okay, so I really appreciate the feedback that I got from the surveys. Question? It was part of your due Friday homework. So it closed like before class on Friday morning. So that's going to count for a bonus point on this week's quiz if you did it. I did get some good feedback. Some of the main things that I'm going to hopefully be able to address are things like answering homework questions either in recitation or not necessarily answering questions, but making sure that we get some feedback on homework. I got maybe one or two requests about going over test questions. I just want to reiterate that that's something that we can do in office hours one-on-one. So take advantage of my office hours, Mark's office hours, Marissa Bell, to talk about the test. I can't give them back to you. I'm going to hold on to them, but we can absolutely, and we should, talk about your test. So please take advantage of that. But I was glad to hear that you guys are taking advantage of the videos and like that. And so for the most part, I got some really positive feedback. So I will continue practicing the technology. I'm sorry that I'm not always the best at that, but I'm getting there. I think I'm improving. Yeah. For homework, I don't want to commit myself to that yet because time is already painfully absent in my life. But I'm going to make an effort in a direction to make sure that you guys get the feedback you need on your homework. Okay? I don't know what that looks like yet. I'm still brainstorming. Okay, so I think we are ready to get on this. So let's do it. So today we are going to pick up where we left off on Friday. And so I want to, at the sake of being repetitive, that was another comment I got. But so why am I being so repetitive sometimes? For people like you, but I mean for everybody, right? Because that's how we learn, right? If we repeat a certain way of reasoning, that's how it becomes secondhand to us. So I'm trying to drill in these ideas. And I think one other comment I got was like, why are we learning stuff that we should have known from pre-calculus? Well, not everybody took pre-calculus here and had the benefits of Mark's way of teaching. So I want to make sure that everybody got to the same page. So hopefully now we are all on the same level and we can progress forward with some of these really fantastic calculus ideas, okay? So all right, so the idea of integration. What are we looking at? We're looking at the value or total change of a quantity that can be calculated. Whoa, no, that's not what that was supposed to look like. I even just said that I was going to get better with this technology thing. Okay. The one slide I didn't rehearse. All right, so the value or total change of a quantity can be calculated as the sum total of many little bits of change. Okay, so we are going to build up this accumulation function idea, which is nothing more than talking about a quantity function that we think of as being built up from little bits of accumulation. Okay, so when I say accumulation function, what should come to mind is things like our tax function that we had talked about, where we could think of, having an output of tax due on, your annual income. But we can really think of getting to that by thinking about incremental accumulations of tax due, right? So when it came to the tax function, we talked about, breaking it down in terms of each dollar that I earn, how much tax is due on that dollar. When it came to the height of the ball, what were our increments? Were we doing so the height of the ball after X seconds, we talked about height accumulating in increments of what? Do you remember? Was that too long ago? So we were talking about the rate changed in half-second increments, right? So every half second, the rocket fired, and the rate of change increased by 1 foot per second, I think it was. Okay, so here our increment size was half a second, right? Up here we had $1, And so, we can choose how big our increments are, but just keep in mind, right, that we're trying to get at this idea of little bits of change, okay? So I could have talked about, 2-second intervals if I'd wanted to, but that probably wouldn't have been as productive considering the setup of the basketball problem, okay? Okay, so now for homework due today, you had this picture, right? So I was just kidding. It was in the document. So what was the problem about? Okay. I made all of these glorious promises right at the beginning of class, didn't I? Okay, so let me just bring it up really fast so that you... Okay, so we had a bacterial culture that starts with 100,000 bacteria. Okay, so the graph below shows the rate measured in bacteria per hour at which the number of bacteria grew at each moment in time, measured in hours, after the culture was first observed. The rate fluctuated because the culture's environment fluctuated, right? That's pretty typical, I think. Use the method illustrated in this section to sketch a rough approximation to a graph of the number of bacteria in this culture at each moment in time for the first 2 hours after being observed. Represent changes in the number of bacteria symbolically in terms of delta X and delta Y, as well as graphically. Okay, so that's the setup. So we've got this bacteria culture. We are mad scientists, and we are growing bacteria. We start with 100,000 bacteria, and the rate of change of bacteria in the culture is given by this graph. Okay? So far, so good? So that's the setup. So what I want to do is sort of like reflect upon what we've done before and see how we can apply it to this scenario. So for instance, when we had the basketball problem, right, we had like a rate of change function that looked like, we had these little steps, right, these little, we called it a piecewise constant rate of change function because it was literally made of pieces, each of which were constant, okay? But here we don't have that scenario. So if we want to apply the tools that we've previously developed, well, let's superimpose them, right? If you have a strategy to solve a problem, use it, okay? So if I want to talk about this scenario with this rate of change, I don't have the tools to deal with the fact that the rate of change is changing, right? But what I could do is say, well, let me approximate the rate of change, okay? And I'm going to do that by creating a piecewise constant rate of change function. It's not going to be arbitrary, though. I'm not just going to randomly pull it out of a hat. I want it to actually approximate this curve. So what I can do is say, well, maybe for now, let's start with chunks of size, or intervals of size 0.4, okay? So let's see, so here is 0.4 here, 0.8, 1.2, 1.6, 2, right? And I could keep going, maybe I shouldn't have kept going. Where are we at? Over here, okay. And then what can I do? So for each one of these values, or each one of these intervals, I'm going to take the value of the function and make a piece of constant rate of change, okay? And so for the first interval, it'll be down here. For the second interval, I'll find the value of the function, and I'll create another piece. Here, there's another step. Here is another step. So are you guys seeing how I'm creating this? I'm going to the right endpoint of the interval, and I'm finding the value of the function, and I am using that value to create a constant rate of change over the interval of length 0.4 that preceded it. Okay. So now we're in a scenario where we're looking at a piecewise constant rate of change function. Why is this useful? What kinds of things might I be interested in talking about if I am growing bacteria in a culture and all I have right now is the rate of change? Mm-hmm. Right. So the whole point in having a rate of change function is for, like you can figure out how it's growing or decreasing in population, basically. So I could look at this first interval. What's the rate of change that I've drawn in here for this first 4/10 of an hour? It's about negative 500, right? Is that the number of bacteria? Is that how much the bacteria has decreased in the Petri dish? Or increased? What does this number represent? The change in number of bacteria. What are the units on that? So this is bacteria per hour, because this was in hours down here, and this is bacteria per hour. Okay, so, all right. And then let's say this, what's this next one? About negative 200. This one's about, we'll say 150, maybe negative 50 here, right? So these are the rates that we're using to approximate. Are they very good approximations? Are we going to get a really, really like rock solid, hey boss, guess how many bacteria I have in my Petri dish? Say that with confidence? Probably not, right? Okay. In particular, for this first 4/10 of an interval, is this negative 500, is this approximating more bacteria than will actually be there, or fewer bacteria than will actually be there? At the end of 4/10 of an hour. You want to take a second to talk to your neighbor and come up with an answer? So what I want to know is, if I use this black bar to approximate the rate of change for the first 4/10 of an hour, will it spit out a total number of bacteria that's greater or less than the actual number of bacteria in the Petri dish? So take a second, talk to your neighbor, come up with an answer. And I got my list back. I lost it all last week. So, okay, here we go. Penny. Are you here, Penny? So do you have an idea? That's okay. So I'm curious. So I will, using the black bar to approximate the amount of bacteria, produce a higher number or a lower number than the actual amount of bacteria? Higher. Do you have a reason? Not really. Okay, that's okay. Annabelle? Less. And your reason? Oh, okay. So you're taking issue with that the point was actually higher than the 500 bar? Okay. Well, let's say that it was actually 500. Still have the same argument? Okay. Taylor? Jay? Mm-hmm. So here, or oh, you're going all the way over here now. Okay, so let me remind you that we start the whole scenario with, I think it was 100,000 bacteria. Okay, and then this graph is the rate of change graph for the bacteria. Okay, so let me erase this because I did actually prepare this to do hours. Oh, and then bacteria per hour. Okay, so then I just erased over the hours. So what happens now? So this graph is telling us how fast the bacteria population is changing at any given moment in time, right? Rashay, did you want to say something? No? Okay, you just looked like you were thinking about it. Okay, so does anybody feel like they have a convincing argument one way or the other? Yeah.
So if the rate of change is negative, it's going to be no matter if it's -1 or -500 or even if it's increasing, like the graph is increasing.
Over here?
It's still in the negative.
Uh-huh.
So it's going to have a negative net change.
Okay.
That's why you go to the positive and you have a positive net change.
Okay, so right, so let's just analyze this graph for a second. So over here, the graph is negative. So that means that the bacteria is actually decreasing in number. Right. So like as we move this way, it's decreasing. It's just decreasing at a slower rate, right? And then here, the number of bacteria would be increasing. And then over here, the number of bacteria would be decreasing again. Yes? Point of inflection? What is that? I have no idea what that means. No idea. So if we wanted to analyze like where, so I don't know what point of inflection is. I don't want to go into that right now. I know what it is. I don't want to talk about it right now. No, okay, so right, so what's going on? So here the bacteria is decreasing, but up until about this point, then the behavior will change. And it has a special name, a point of inflection. But we'll visit that at a later date, okay? Don't be too sad, I promise. It'll be okay. Now I lost my train of thought. That's okay. So out of curiosity, just for the sake of like thinking about what's happening, because I'm not convinced that we all understand what's happening here. Like, when will this bacterial culture, like, what is actually happening? If I start here, I have 100,000 bacteria. And then the numbers do what? They go down, right? And they keep going down until 1 hour, at which point they start to climb again. And then, at like 1.6 hours, then they start to decrease again, okay? So if I'm decreasing during the first, my numbers are decreasing during the first 4/10 of an hour, right? Are we, yeah? So this graph is still negative here. So be careful. This is the graph of the rate of change function, right? So the y values are bacteria per hour. So if I pick a point right here, okay, so this is the point 0.7, comma, negative 400. What does that point mean? Yes? So 7/10 of an hour after paying attention to my bacteria, the rate of change of the bacteria is negative 400 bacteria per hour. That's not an amount of bacteria. Okay, it's how fast it's changing. So if my actual rate of change, yeah, do you want to say something? Mm-hmm. Mm-hmm. Yes. Uh-huh. Okay, so you're going really fast. You slam on your brake, and then but you're not. No, 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 no. We're not speeding up here. We are not speeding up here. We are still slowing down here. We are still slowing down, just not as fast. Okay. So like maybe you're letting up on your brake, but you're headed downhill. Okay. Uphill. Sorry. Okay, we are still slowing down here. Okay. And then this is where we would actually start speeding up again. Or, I mean, I said that wrong. We're going faster. Okay. Hmm? Mm-hmm. Yes. So so what's going on here is that the number of bacteria is still decreasing, just at a smaller rate. Right. Okay. So like over here, I'm only decreasing by 100 bacteria per hour instead of 400 bacteria per hour. Okay. So if this is the rate of change, the actual rate of change function here, and this is my approximation, what's going to result in more bacteria? Decreasing at a slower rate for a while and then getting down to the rate of negative 500, or decreasing at a rate of negative 500 for the whole interval? What's going to result in more bacteria? More bacteria total in your petri dish. The actual rate of change, right? Because I'm decreasing at a slower rate throughout here, right? My actual rate of change function has a higher value than it does with my approximation function. Mm-hmm.
But would the approximation function, like, could you make the line from the origin to the approximation value? Because that's the other thing that can happen.
Oh, I mean, you could approximate any way you want,
No,
but this is
that what we're doing?
that's not what we're doing.
Okay.
I'm creating a constant rate of change.
Yeah, I know. From where? From what point? Sorry.
From the right endpoint at the value of 0.4, I found.
It's just an isolated rate of change as opposed to a constant rate of change over a period of time.
Oh no, this is a constant rate of change over a period of time, because what I'm
What period of time to what period of time?
from 0 to 0.4 seconds.
Yeah, so it would be a straight line, right?
But it's not diagonal. It's horizontal. It's a constant rate. Okay. So I pick the value by looking at the graphs, the actual rate of change. I look at its y value, and then I take that y value and I extend it throughout the interval. Okay. So over here, I took the y value at 0.8 and I extended it throughout the interval. Okay. How are we doing? You really have to think about this, right? Yeah.
Yeah, when I was doing the homework, I thought that those horizontal lines were supposed to represent time rather than concentration.
Well, so the horizontal line itself it's a change in time, but the value of it is the value of the constant rate of change. That's a good clarification to make. Mm-hmm. Yes. So the actual rate of change, the purple curve, is smaller, right, throughout this interval than the approximate rate of change. So that means it's decreasing. When I say smaller, I mean closer to 0, okay? So that means that the number of bacteria is decreasing more slowly in actuality than it is with this constant rate. Mm-hmm. Right away. Yep. That was really a good summary. Did you guys all get that? Can you say it really loud, or do you want me to say it? Darn. You said it so well. Okay. So if we use the actual rate of change function, the bacteria is changing. It starts changing at a small rate, right? So initially, it's changing at a rate of 0 bacteria per second, or per minute, or hour, right? And then it'll like become, negative 100 bacteria per hour, and then it'll become negative 200 bacteria per hour. But it's changing slowly at the beginning, as opposed to if we use our approximate rate of change, then it's instantaneously changing at a rate of negative 500 bacteria per hour. So it's already changing, like decreasing in numbers really fast right from the offset. Okay? Yeah? Okay. Oh boy. Okay. That took approximately 20 times longer than I thought it would. So this is good though, because we're really getting it. So, okay, so what was the point of going through all of this? To create a function where we have pieces that are constant rates of change. If I have this information, yeah? So I could increase my accuracy by decreasing the size of my intervals. Absolutely. And that's where we're going to go. But first, I want to keep the big picture, which is why are we doing this in the first place? Yeah. So we want to pretend constant rate of change that behaves nicely meaning piecewise constant rate of change. Because if I have this scenario, then I can create an accumulation function that will be piecewise linear, that will give me an approximation for the actual amount of bacteria at any given point in time, right? That's where we're going with this. We want to know how many bacteria are in my petri dish. I want to report back to my boss, right? And so I can't do that with the curve. I don't have the tools, but I do have the tools if I have a constant rate of change function. Better if it's a piecewise constant rate of change function. Okay, so what could I do? I could take each of these pieces, right, these constant rates of change, and I could actually compute the amount of change in bacteria. So for the first interval, right, so X is time, B is bacteria, okay, so I start with 100,000 bacteria. After 4/10 of an hour, how am I going to compute that number? So this number times rate of change? So the rate of change times 0.4. Okay, so this quantity by itself represents what? How much change in the first 4/10 of an hour, right? But I'm not asking for how much change. I'm asking for the actual amount of bacteria. So in order to get amount of bacteria, I need to do the amount of change added to the original amount, right? And then if I wanted to do it again at 0.8 of an hour, well, now I've got for this, for the second interval, if you will, my rate of change is negative 200. So I'm going to have negative 200 times, is it going to be 0.8? It's still 0.4, right? Because that's the size of the change in x. That's the delta x. So this is k delta x plus, now what am I adding that to? whatever I got from this thing, right? Oh dear. Oh, can we give it a name? Okay, I like that. So, well, how about we say B of 0.4 since I called it B? Okay. Okay. So, all right. Is this making sense? Okay, so then if I wanted to make it better, like we said, we could make the size of the interval smaller, right? So this is now a better approximation. What else has changed besides the fact that I've gotten better approximations? So the smaller interval is what I'm talking about when I say better approximation, because now our steps, if you will, are closer to the actual rate of change function, okay? But what else has changed? Well, so yeah, so that's the smaller interval, and my changes in x are now 0.1 instead of 0.4, which means the corresponding changes are smaller. Yeah? So all of this means my approximations will be more accurate. Absolutely. All of this is true. What I'm asking for is a very subtle point. It's super subtle. How did I create my steps on the last graph? Oh, so on the previous graph, I built my step function, if you will, by locating the right endpoint of an interval and tracing back the value. How did I create this one? I took the starting value of the interval and then traced out the value, right? So I'm pointing this out because you're going to be reading about these step functions in your homework. And what I'm going to be calling them is left x, mid x, and right x, where the left is this one, okay? We use the designation based off of where the value of the constant rate comes from within the interval. So on this one, it's the left endpoint that determines the value for the entire interval. Okay? And if I had wanted to do a mid, right, then I would find, let's see, so like this interval right here, I would take the midpoint of it, I'd find the value of the function, and then I'd trace it out up there. Does that make sense? Okay, so I just want to clarify that so that you won't, so it'll be a little bit familiar. Okay, but so now I've got these smaller delta x's. I've got better approximations, right? For every change in x of 0.1, I can record the rate of change at the left endpoint of that interval, right? So I've got all of these rates of change, and then I can come up with a total rate of change by looking at the rate times delta x, right? So each of these is going to give me a change in population. I add them up over the entire interval. That'll give me a total change, right? So I can do that. And then I can use that to actually create an accumulation function where this is actually showing the amount of bacteria now in my petri dish from the rate of change that was given. So this is the actual accumulation function.
It's off by a factor.
It is off by a factor of, yeah. Okay, so then that's how that all works, right? This is the idea. But holy crap, you saw all that writing, okay? And what's to note is that was an approximation taking delta x's of 0.1. That's still not that good if you're a scientist. You want much more accuracy than that, right? So what would be the next step? Instead of going by changes in 0.1, you'd probably want to go by changes of 0.01. Well, now you just crazy increase the number of things that you have to add up, right? So let's actually use the mathematics that we've developed to make this happen, okay? Machines are here to help us, okay? So big picture view of what we're doing. We are figuring out right now how to take any rate of change function, any exact rate of change function, and create an approximate rate of change function that's of the form of a step function, okay? So we're going to create steps where the value of each step comes from the value at the left end of the interval, okay? And we're going to call this a step, we're going to call this function step of x, okay? That's what we're just going to call it. It's going to be our approximation rate of change function. And we get these values, again, by taking the actual rate value of the left endpoint of the interval. Okay, so this is me defining a new function from values of the function r, where r is your rate of change function, your actual rate of change function. Okay. So, but all of this depends on actually being, I mean, this is not really mathematical language. Can we all agree with that? Me writing the left end of the, no, that's not how we roll, okay? So what we need now is a way to actually calculate mathematically the left endpoint of the delta x interval that our current value of x is in, right? So like if I were to, you know, highlight this x value, how can I automatically spit out this value, right? The value at the left end. Okay? So that's our goal. So let's get to it. Okay, so here I've got the graphing calculator file where can you all see these red dots? So my red dots start at an initial value of a, and I've got delta x intervals of length 0.8. Okay, so these are just marking every interval. Okay, now I'm going to be able to move this blue bar, which is going to be my current value of x. And what I want you to do is come up with a way for no matter, well, let's do this in particular first. Okay, so right now, my current x value is 3.22. How could I compute the left endpoint of the interval containing this current x value? You want to take a minute and talk to your neighbor about it? Come up with a strategy. So find the left endpoint of the interval containing the current x value. And the current x value is 3.22. Okay, and so these are your tools. You have an answer? You got quiet. I don't know if that means you got your answer or you got stuck. Silence. Lauren, are you here? Do you have an idea? Uh-huh. Oh. Okay. Yeah, so remember, we're not about the answer, we're about the process. So, okay, so it looks like it might be 3. That might be an unfortunate coincidence. I should make the numbers harder. I will on the next one. Okay, but maybe it'll be okay that if the numbers are easy. I don't know, is it distracting that the numbers are easy right now? Okay, so what's the process? Ooh. Yeah, I know. But they've already thought about this one. So, how do we get there, though? No, I really do want it in a different interval, actually. What do you think? No? You have a process?
I think so.
Okay, tell me what your process is.
Take your n divided by your delta x, round it to the round it down to the nearest integer.
Take my current x value, right? That's what you just said.
Right, you're at the m, right?
Okay, divide it by delta x.
Right.
So you want to take, so this is n, starting at 0.
Oh, okay.
But remember, we're starting at -1.
Right, so
N plus a? How, so tell me what you're actually trying to do.
So get how many steps you've done.
How many steps? How many intervals, right?
Intervals,
Okay.
and round it down to the nearest integer.
Okay. So okay. I like where you're going. I like this process. Okay, so you want to count the number of intervals. So there's 1, 2, 3, 4, 5 intervals. Okay, but you're saying that we can do that effectively by doing what?
Dividing the total intervals by how many steps we take.
Okay, so if I take the total distance, how do I compute that total distance? So current value, which I'm calling x, it is n, but I'm going to call it x. And to find that length, I should do n or x plus a? Did you just say that because I said plus a? Like, really? Why is it minus a? Why is it minus a?
Oh, because that's your total. You're always going to have your x minus your a. That's what we learned.
Oh my God, it's what we learned. And you thought it was silly. We talked about multiplication and division. Okay, so how do you find a total length? Final minus initial, right? A change in distance. That's what we're looking at. Changes we compute by doing subtraction, right? That's the operation. Okay, now if I want to then figure out how many intervals I can divide by the length of each interval, division, yay, okay. But if I only take this number as it is, that could potentially give me a decimal number, right? Not a whole number value. So you actually said it beautifully. You said, but I don't want the decimal. I want to chop off the decimal. I want to round down to the nearest integer. Mathematics has a thing for that, okay? And it's called the floor function. And you denote it using these symbols, okay? So this is called the floor function, and it does exactly what we want it to do. It takes this number, okay, and it chops off the decimal. Yes? So because I want to know how many intervals, how many complete intervals I have progressed through from my initial value, okay? So far. We are so not done with this, okay? This is literally, we have now computed the number of intervals. Why did I want to compute the number of intervals? So to get to this, right, so remember, my goal is to figure out what this x value is. So I've got the number of intervals. That's not enough. What do I still need? To multiply it by the length of each interval. We're still not done because where did we start? We started at A. Okay, so if we start at A, our initial value, then we go some number of intervals of length delta x, and that will land us at the left endpoint of the current value of x, okay? But where the trick is figuring out how many intervals of x. Well, if you take the total distance between the initial value and the current value and divide that by delta x, that would tell you what? That would, I mean, so what, we studied all of this relative size stuff, right? So that's going to tell you how many intervals plus a little bit, right? So in this case, if I take this x value, right, 3.22, subtract off a, and divide by 0.8, I'm not going to get an integer, right? Okay. Does anybody have a calculator? Or I guess I could do it here. I don't remember at the moment. We'll get there. Okay, so I take this and I divide by 0.08. Oh, not 0.08, just 0.8. Okay, so that gives me 5.275, right? So that goes along with the fact that, you know, to get from here to the actual x value, I go 1 interval, 2 intervals, 3 interval, 4 interval, 5 intervals, and then a little bit more. Where did my red dots go? Oh, wait. Oh, they're there. Why aren't they graphing? Graph. There we go. So, okay. So I want to chop off that extra little bit. You know, it was 5.275. I don't want the 2.75 because I only want to land where the green is. And the green is the left endpoint. Does that make sense? Let's try it again. Okay. So let's change, you know, let's make this 1.2, and this is going to be like 0.67. Okay, so now the numbers aren't as easy. Okay, and I can move this. Okay, how are you going to find? So my current x value is 6.22. So I'm trying to find the left endpoint of the interval containing this x value, right? So I start at my A, and then I have to figure out how many complete intervals there are leading up to it, right? Now I can count here, but again, I want to generalize. So instead of counting, I can say, oh, well, let me take this value and actually compute what this all is, right? Take the integer value of that and multiply it by the lengths of the intervals. Okay, so this quantity here is literally representing the distance from here to here. And then we're adding it to the starting value so that we actually land at the end, right? This is our goal, is that value right there, okay? So in general, we can define a function called left of x that takes an initial value and some fixed length of interval and will spit out the left endpoint of any current value of x. Okay. All right. So on Wednesday we'll pick up talking about why we did this all over again. Okay. It does. It's like 6 foot of x. Again? Maybe. Okay. Let me look. I know I pressed record. Hold on. I have to find it. There we go.